In today's day and age, what new content can possibly be delivered about Strider SNG knives? What if I told you that when I put my thinking cap on and armed myself with a set of calipers, I discovered a whole slew of features that make this knife relevant even by the modern standards? In this video, we will take a microscopically close look at the edge geometry, check the hardness of this MagnaCut blade, and find out why some of these knives feel so tight and what you can do to make it more user-friendly. So what makes up a Strider? Without trying your patience, I will tell you upfront that this lock bar with its unprotected face is the key suspect behind this knife's criminal inability to be flickable. Not to mention this pocket clip, which is a blast from the past, better at shredding your jean pocket than actually facilitating insertion and extraction of a knife from that pocket. Fortunately, this problem is easy to fix, and I'll show you the solution at the end of the video. The superpowers of this knife lie in its hardware. These titanium spacers and strong, powerful T10 screws. We'll have plenty of chances to talk about the spacers and the screws. For now, let's just take a mental note that the only pieces of metal that contact both halves of the frame are these spacers. T10 screws can be torqued to an immense 33 inch-pounds. This is a primary feature of this knife in the order of its importance to the overall design. It's called thrust pivot. The male side has 1/8 inch Allen or T15 socket that opens up to a smooth bore, which is a locating feature for the assembly tool. And this pivot nut is key to everything. When I place it into the blade, you can see it doesn't just drop in easily. That's called slip fit. So whatever the diameter of the hole is, this is undersized by not more than a couple tenths of a thousandth of an inch. The reason people design it that way, to minimize rocking. So when I engage the two, there's very minimal rocking, and so all the forces that generated at the blade, they're transferred to this component here. That means even if the pivot comes loose, loosens up during use, which does happen, the blade will not rock either side to side or up and down. And I can show you that using this knife. I bought an inexpensive tool and I had to modify to actually make it work properly with a Strider. You have choices for the driver bit. You can use 1/8, 3mm, or T15 bits. So I'm loosening it up, and it's not an easy task, especially if you have any Loctite on the threads at all. So perhaps consider not using Loctite. We'll talk about all this in a little bit during the assembly. So now this moves. There's at least, 8 thousandths of an inch movement here. So this pivot hardware is loose, but let me lock it properly. But there is no play here. No play. Reason is that immense bearing surface. So this knife will function even when it's not fully tuned up. The reason it feels tight is how, not the detent ball, but how the actual lock bar engages the blade. The future me decided to go on a small tangent here and give you a short segment explaining why Strider doesn't drop shot easily. Remember, this is a fully tuned knife, fully broken in too. So, and why doesn't it flick? See how it stops right there? Without some amount of wrist twist at the end of the motion. And to do that, I asked an old friend to pay a visit. This is McNeese PM, which is similarly constructed, has a lot of similarities to the Strider, but it's a near perfect flipper, and the blade drops shot easily. The reason that's happening is John McNeese minimized the contact between the lock bar and the blade. As soon as you break detent, whether you're going to open the knife, as soon as you break the detent, nothing touches the blade but the detent ball. It's like a single ball bearing, or bearing with one ball that rides on the blade, and so the friction is minimal, allowing it to go all the way out, and as soon as that ball jumps off the tang, it's in the locked position. So at no point does titanium on the underside of the lock bar contact the flat surface on the tang of the blade, which is completely opposite of how Strider operates. Initially, when you break the detent ball provides a single point of contact for minimal friction. But as soon as it jumps off the tang of the blade, right there, there is still 30 degrees of traverse, during which, let me show you up close, the edge of this titanium lock bar rides fully against the metal of the blade. See that pie-shaped section that I'm bordering off with my fingernail? Pretty good slice of a contact area. I estimate that for the last 30 degrees of rotation, the lock bar edge is in full contact, and that is like hitting the brakes. In this analogy, the blade is the disc, and the lock bar is the caliper. So that's why you need to add this a little extra velocity by flicking your wrist. You can see actually this shiny line here. It's the lock bar getting sort of worn in or broken in when it engages the blade. Right now this blade is perfectly centered, and that allows me to run this lanyard in a monkey ears attachment pattern. I know my viewers are wondering how hard this MagnaCut blade is. My concern is it's Cerakoted, and when you Cerakote a blade, you subject it to high temperatures, which can actually reduce the hardness of the blade. But first, I'd like to speak of the disassembly tool, which is kind of a must-have if you own Striders. I spent less than $15 on Amazon for this tool, and I added this central stud to engage. Let me show you here. So when these are together, this side has a hole. The hole measures about 1/8, or it's actually very tightly 1/8. So I drilled a 1/8 hole in the front face of the tool and hammered in a roll pin that was 1/8. And then I had to downsize the roll pin a little bit using a Dremel. And now they're engaging properly. And that centers these tabs to the slots. Otherwise, the tool can slide out of the slots and scratch your scales. See this? This one is on me because I was using it without adding this aligning feature. And then I added this sliding handle, which I made out of 4mm roll pin. And I flared it out on the end so it doesn't come out. For $15 and some elbow grease, I got a very workable tool. There's, of course, a bunch of other offerings out there in the market. But if you are on a super budget, this is a good option. I'll throw a link in the description, and that link will benefit my channel. So thanks in advance. All right, let's move on to the hardness test. What you see on the right is the dial on my benchtop Rockwell tester. On the left is the anvil. And here is my calibration plate. It's NIST independently certified to be at 62 HRC almost exactly, 61.99 to be precise. I do this calibration check before every Rockwell hardness test that I film in order to avoid any confusion in the future and to keep everything on an up and up and in the open. The occasional shimmy you see, it's me bumping into the tripod. And so this is me zeroing the dial. As you can see, the small hand is in the middle of the red dot. The long hand is right on the letter C. And right now, I'm allowing 10 seconds for the full load application. It's a 150 kilogram load. And now release the lever. 62.1 is the result. We are in tolerance. This blade is made out of MagnaCut, which is a jack-of-all-trades stainless steel. Due to its highly balanced performance in toughness, edge retention, and corrosion resistance. The typical range for MagnaCut is 60 to 65 HRC. On the lower end of the range, between 60 and 62, you will get the highest corrosion resistance, where between 63 and 65, you get maximum edge retention. Most manufacturers are trying to hit 62 to 63 range. The toughness stays roughly the same, very low sloping curve there for toughness, and that's why it's considered to be a very well balanced steel. Before we go any further, I'd like you to know that my method is not industry standard, because even though I'm using an industry standard device to measure hardness, I am testing a sample of 1. For small batch production, a sample of 5 is required to statistically determine hardness for the batch. And for larger batches, a sample of 20 is required. All right, what we got here is 60.7 on the first poke. Let's do 2 more pokes. All such measuring equipment has built-in error, and the standard for Rockwell testers allows plus or minus 1 point accuracy and plus or minus half a point HRC repeatability. So technically you can get plus or minus 1.5 point error, which seldomly happens because these devices are calibrated, and when they're calibrated properly, you expect a much smaller error. That said, the second poke comes in at 60.7 HRC again. By the way, if you enjoy my meticulous testing, please hit a like, or if you're not a subscriber yet, please subscribe to my channel. So let's talk about this specific blade. As you recall, it has HC treatment, which stands for heat coloring, and then the tiger stripe pattern is applied via Cerakoting. Both of these processes require application of heat, post-heat treatment. So typically, and unless the bladesmith plans to heat treat a little bit higher so that they can apply those heat processes, the blade's hardness drops by up to 1 point HRC because it's like an additional tempering. Being one of the top most stainless steels in the world, MagnaCut doesn't really require extra finishing. And yet again, we're at 60.6 HRC. And on top of all this, there is still a debate in the knife community whether or not this reduction in hardness occurs just at the surface or permeates the entire thickness of the blade. So this blade and this blade only is at 60.6 HRC. The big question is, what will you get out of this blade performance-wise? According to the MagnaCut's inventor, Dr. Larry Thomas himself, the performance of the steel in toughness category will be on par with A2 or CPM M4. As far as edge retention goes, it will be similar to D2 and CPM 154. Corrosion resistance will be between Vanax M20 CV or M390, which is basically the same steel. We interrupt this broadcast with a big news. I was able to obtain another Strider SNG, and that's how they come brand new from the factory. That's the shipping packaging on them, minimalistic. And this one is also a MagnaCut unfinished blade, and it has a G10 and titanium double gunner grips. But I'm excited because that gives me an opportunity to test the unfinished MagnaCut and at the same time test my theory that applying the extreme finishes that Strider does change the hardness of the blade, at least near the surface of the steel. The hardness test for this blade will be at the end of the video. I'm trying to come up with the most accurate way to measure behind the edge thickness. So the plan is to place the blade on this flat anvil where the dial indicator is zeroed. I'm going to place the blade onto this surface, pressing the primary bevel tightly to it, and then bring it in, and the gap under the apex you see, it's the other side of the secondary bevel being slightly elevated. And now I'm measuring right behind the edge. So what I couldn't see until I edited this segment is when I pressed down on the blade, the anvil went down by about 0.02 of an inch because the base of the indicator is not on the same surface as the anvil itself. A mistake I'll fix next time. But if I get 23 thousandths, consider it 21 or so. So we'll call it 20 thousandths plus or minus 1. And my last measurement was 19 thousandths. So right there, 20 plus or minus 1. And now it's time to reassemble the SNG while taking full advantage of the knowledge I gained while poking around the design of this knife. Before starting the reassembly, I secured all the hardware to the frame halves with a sticky tape. So let's talk hardware. These standoffs can vary in height. Let's measure them and keep track of each individual one. This one is 203 thousandths of an inch. This one, what have we got here? 205 thousandths of an inch. And this one is 206 thousandths. And now I am going to start assembling. I'm going to put the tallest standoff in the front, the middle in the middle, and this one will go here. This one I'll have to flip over, so I'm going to put a dash of sanitizing gel on the inside so it stays on this little stud, and then the gel will just evaporate eventually. So now I can put my now polished washers, first one on, now the blade, and the blade goes into full open position against so the stop pin is against the frame and the other washer. I'm going to flip it over and try to line it up. I also have to mention that I bore brushed the pivot hardware to remove the old Loctite that might have been there. And so now I am lining all these pieces up. You might want to pull on that bar, and I am going to start here at the pivot. If you are enjoying this video, please hit a like right about now, or better still, hit the share and copy the link to the video. First you have to go all the way in and then make sure the reverse side is still flush with the handle, with the frame. And now pull on that bar and line up the middle standoff here, and use your T10 to thread that in. But don't tighten it yet. And sometimes just holding it on the back side helps, but if it goes too, if you feel that this rotates, you just need a second T10 bit. That's why I always have two sets of multiple bit drivers. And again, this doesn't need to be tight at this time. You saw me backing up. Now I'm going to throw this screw in here on this side. Okay, and this screw I can actually tighten and torque all the way. I'm going to say about 30 inch-pounds of torque is sufficient, but I am keeping this guy still completely loose. And I'm going to put this guy in. Make sure. Yeah, looks like I need to thread it on both sides. I hear reviewers complain about not having captive hardware. In the case of this knife, it would be counterproductive because you can torque the T10 screws to the appropriate torque value. So remember, this standoff is the shortest and this is the tallest. So if you were to measure, the halves of the frame would flare out like this, just a little bit. We're not talking a lot. So from here to here, about a thousandth of an inch. So from here to here, another thousandth of an inch. Now I'm going to back out this guy. I don't want it super tight. And just making sure there's no compression at this point yet. And I double check that I torqued here. Still torqued. And now I'm going to torque this guy. So friction torqued it. Let me double check here. We don't want to leave anything to chance, do we? Yep, we're torqued. Now I'm going to check the function. Very freely moving right now. Yep. So now I have to torque this. Here I'm going to go snug, but not super tight. Check for function again. Can peel that off. Make absolutely sure you are flush. You can push it in flush, because if you couldn't, that means you are catching the bronze washer somewhere, and you don't want to deform that washer. They're hard to find, hard to replace. And so now I am going to tighten it here. Okay, and check for function again. Now it starts to feel like Strider. So I'm going to back it out here a little bit. So in the pivot, you want to find the sweet spot where this is not rotating. See, the slot is not moving. Yep, I think we got it. Now you notice I didn't put any Loctite, and there's a good reason. Like I said earlier, if this pivot is loose and even moving a little bit side to side, the knife is still not going to rock side to side or up and down. And if you put Loctite, you're risking getting some Loctite under this humongous flange here on the pivot screw. If that happens, you will probably not going to be able to successfully disassemble the knife. So in this position, it just has to be snug. Let's address the issue I found. Oh, not really an issue, just a little sort of naggy, little pesky concern I have. See how that pocket clip is wearing out a little line here on the handle? That means that it's a little bit too tight. So I'm not planning to bend it. I found this basically shim washer that I'm going to throw onto here. And let me show you. It measures 0.006 of an inch thick. Even a piece of tape helps sometimes. Just putting a piece of Scotch tape, which is about 0.002 or maybe 0.003 of an inch thick, helps to elevate this clip. Now we can torque it in. So now it's not touching. And if I put it in my pocket, it goes in easy. It still has enough tension here at the seam, and you can't even see that there's a shim there. So just a food for thought. Let me show you. The centering came spot on. So I put zero effort into like figuring out how to center this knife. If you do everything correctly, it will end up in this condition, centered and operating smoothly. It's still not a flipper, but check this out. I can actually shake the blade close almost. Come on. There you go. Reverse flick, lots of wrist, but it does it. If you watched this entire 30-minute video just to learn about the hardness of the blade, I would like to let you know that going forward, all the hardness tests will be posted in the channel members only area as short, sweet little hardness test only videos. They will not be available to broader public. The link to the membership is in the description. If you prefer not to purchase it, you can still see all the same tests in long format videos, but a few days after the members. Since there was an interruption between the hardness test, I'm recalibrating my Rockwell tester. Meanwhile, here's the curing temperature recommendations from Cerakote's own website. As you can see, those temperatures can reach 250 and 300 Fahrenheit. The question is it enough to affect the final hardness of the blade when it's subjected to those temperatures. Let's think about it together. 62.0 HRC is actually right in calibration. Moving on, where was I? And to help our thinking process, here's the table that shows austenitizing and tempering temperatures for MagnaCut. And keep in mind, most of these fancy stainless blade steels, including MagnaCut, require double temper, meaning they heat soak them for 2 hours at what's called dwell temperature, and then bring them down at a certain rate, which adds another half an hour to an hour to the cycle. 61.8 is this poke for the blade. I estimate the total double tempering cycle to be at around 8 hours, maybe even more. And let's say there is 200 blades in the batch. Some of them will end up being Cerakoted and some will be left in the white. I suspect the colorization of the blade after temper plays a major role in selection whether it's going to get to be stonewashed or stay as HC. And this colorization also contains important piece of information. This table informs us to what color steel oxidizes due to temperature. And this blows my mind. Apparently, to get these colors of the rainbow, especially browns and blues, they heated this blade to over 500 Fahrenheit. Every MagnaCut heat treat procedure I found online specifically doesn't recommend exceeding 500 Fahrenheit. We can say with certainty this process took place before Cerakote, and therefore I would conclude that Cerakote itself did not affect the hardness. But what about the performance? We're still left with the question, coated or uncoated, which should you choose? I'm not a metallurgist. I hope one of you has enough knowledge to help us decide now that we know that this specific blade is at 60.6 and this one is exactly 62.